God, what's going on?
We can hear you.
Hello, can you hear me?
Yes, yes, we can hear you.
Okay, cool. I thought, yeah, I look at the schedule. I thought I'm the fourth one though. Okay, but let me share it. Are you able to see the slide? Hello?
Yes.
Okay, cool. All right then. So my name is David Wong from New Jersey Institute of Technology, and today I'm going to present our new automated program repair tool named Deer. Change the slide. Okay. Okay, so basically, we all know that the developers probably will spend a lot of time on fixing the software bugs, and so therefore they definitely will need some help. The researchers from industry and from academia have proposed a couple of different automated program repair tools to help developers. With the emerging of deep learning, it has been applied to the APR problem, and they achieve very good results. However, there is still one key limitation, which is that none of the existing deep learning-based APR tool that can auto-fix the bugs was dependent changes to multiple statements in multiple hunks at once. So therefore, to overcome this limitation, we propose a Deer, and we want to sell three key ideas in Deer. So the first one is we want to develop a novel approach that can enable any traditional FL to detect the hunks that need to be dependently changed together and identify consecutive suspicious statements in the hunk. Specifically, we propose two algorithms under this idea. So the first one is we want to identify the hunks. So this algorithm will take the list of suspicious statements from fault localization as an input and will spin out groups of hunks that need to be taken care together. Then after that, we propose the hunk expansion algorithm because we want to identify whether there are multiple statements inside a hunk that need to be fixed together. Then the second idea is we wanted to propose a model that can learn to create fixes or patches for multiple hunk and multiple statements bugs. Specifically, we employed divide and conquer strategy to learn to map into M statement changes, because sometimes when you fix a bug, in the buggy version, you probably will change the M statements to the N statements in the healthy version. And after that, we enhanced the design and orchestration of a train model in Delphix. That is a XC20 paper with a new attention layer and a cycle training to fix multiple subtrees at once. Then the third idea is we want to train a model that can learn the correct surrounding fixing context. So based on these three key ideas, so this is the architecture of Deer. So basically, the first part in this picture is not a part of Deer. That is default localization. It takes the source code and test cases and spin out a ranked list of suspicious statements. Then will take the list of statements as input and also will send it to the expansion algorithm. Then the outputs are a list of hunks with multiple statements. We also train the two models. One model is to learn the context. The second model is to learn the actual change, the bug fix. So, and after that, we also applied some post-processing, like a program analysis-based filters to rule out any invalid patches. Then we also propose a deep learning-based re-ranker that help us to identify the suitable candidates. So that's the overall architecture of Deer. Then we did a couple evaluations to compare the Deer with existing deep learning-based tools and also with the traditional pattern-based tools. So in RQ1, we compared it with the deep learning-based tools on the D5OJ dataset, and we compared it with the most recent achievements in deep learning-based APRs, such as QWare, which is a XC21 DL fix, which is XC20. Then in RQ2, we also tested on the large data sets. Specifically, we evaluated on 2 large data sets. One is big fix, the other one is CPAD minor. Then the baselines are the same as in RQ1. In RQ3, we compared it with the pattern-based tools. Also, for example, like the top performing one, which is the Hercules and T-bar. These are most recent achievements in the pattern-based tools. So here is the results of RQ1. We compared the DEER with deep learning approaches on D504J. If you see the pointer finger here, we basically, the DEER can auto-fix the most bugs and generate the most plausible patches compared with other existing deep learning-based tools. Then we also did fuller analysis. We want to show that whether the DEER can indeed fix some multi-honk and multi-statement bugs. So from this table, you can see that compared with the top 3 performing deep learning-based APR tools, we can actually fix some bugs in different locations. For example, like multi-honks with one statement, or multi-honks with multiple statements, or even mixed like multi-honks statements, like multi-honks with multiple statements, or with one statement. So we can conclude that the DEER can auto-fix bugs at different locations. Then here is the RQ2. We compared the DEER with the DL-based approaches on the large data set. And if you see the rectangle here, it shows that the DEER can auto-fix more bugs than any other study baselines at both large data sets. Then the large RQ, we kind of evaluated to compare it with the pattern-based tools, and we can achieve the comparable results with the top pattern-based APR tools like Hercules. We generated more plausible patches than Hercules. So that's pretty much the DEER. And if you're interested, so please like pop up some questions. And thank you so much. That's my presentation.
Thank you very much. So next should be Tufik. No, sorry, I went too fast. Ye.
This week. Can you see my screen?
Good.
So,
thank you.
So hello, and this is Yet. I'm a PhD student from the KTH in Sweden and supervised by Martin. And this is the joint work with Matthias. And today I'm very happy to be here to present our work, Railroad Program Repair with Education-Based Backpropagation. So in the literature of the program repair, it has been typically classified into 3 categories: the search-based program repair, semantics, and learning-based. And our work here is a focus on the learning-based program repair. As the 5 state-of-the-art showed here, there are 2 in common. First, they are based on the railroad machine translation, which is typically to translate the body code to the correct code and treat it as the source code as much as the natural languages. And the second common is they all use the same loss function. The cross entropy loss is also known as the log loss. A little bit background of the cross entropy loss is actually the summary of the softmax inside the softmax, and it's the it's a very strict pairwise token level computation. So if it's a lower value, means that the predict the output is very close to the distribution of the ground truth, which is the better. And the problem is that in the learning-based program repair, there is a discrepancy between the core training objective. We want to learning to generate the compilable then correct patches, and but the loss function is being optimized is really synthetic to based on the pairwise token computation. So here comes our motivating example. There are two patches given here. The listing seed is a semantic equivalent patches, which receive a bigger loss score here. And the listing B is actually the non-compilable patches. We receive a smaller loss score, means that the model favors the listing B, the non-compilable patches, because it has only one token difference and the other has the more token differences. So the reason is, so it explained that we cannot purely to relying on the cross entropy and the pure synthetic as our training objectives, because the code is not string. The code can be compilable and can be executable. So our core research question here is, to what extent can we embed the unique nature of compilable and executable in the loss function? So we propose to use the reward repair. It contains the two trailing phases, the syntactic trailing and the semantic trailing. The syntactic trailing and semantic trailing are used alternately when the syntactic trailing has been trained a sufficient epochs of the data. So in here, the syntactic trailing is really like to learn the self-learning, and the semantic trailing is acted more like the examining and the feedback. So in we want to provide quantify the feedback of the semantic trailing. So we decide 4 discriminators here. The difference discriminator. We decided this because we found that there are many the model we can simply to copy the buggy code as the output, and then they can receive a very low loss value, because in the typical set of the buggy and fixed pair, there's only one or a few tokens, or even only one token differences. So the other tokens around are still the same, so they can still achieve the good loss value. But that's something we want to penalty, and we also want to penalty the compiler non-compilable patches. So we have the compilability discriminator, which is executed by the compiler. And to determine the possibility and overfitting patches, we employ the human written test cases and automatically independent test cases generated by EvoSuite and Wendoop. So to define the loss function here, we want to modulate the cross entropy loss function a little bit, because we still want to have the loss function to be differentiable. And then the overall goal is to encourage the high quality patches, the compilable, possible, and correct patches. We adjust that the loss, their original cross entropy loss to be 20% lower, and then we penalty the low quality patch, and to learn change and learn compilable, we increase for around 20% to increase their value. Our experiment set up to evaluate the effectiveness, the compilable, and the impact of the semantic trailing. And we give a quick demo. So this is the demo when we won the 120 divisible J 1.2 bugs there. It takes the input as the buggy code, and then we also the surrounding code there. It outputs the patch and also the ranked information for the first correct patches. Sorry. And as the summary of the contributions, we proposed the reward repair to employ the compilation and test execution information into that work. And our work code and data available in the GitHub, and the change model is available in Zenodo. If we still have the time, to go into the data? But we can go back later maybe.
Okay. Thank you. Thank you very much. So, Maria?
Hello.
Oh, yes.
Screen. Can you see my screen?
Not yet.
Can you see my screen? Hello?
Not yet from my side.
Hello, can you see my screen?
I don't know if you hear. No, we cannot see your screen.
Can somebody reply?
Sorry, cannot see your screen.
Hello, can you see my screen?
Still cannot see.
Okay, can you see my screen now?
Yes.
Okay, perfect. Sorry. Okay, so in this presentation, we want to present our work that it is published in TSC, and we evaluate automatic program repair tools to repair API misuses. So we know that in the literature there are many available automatic program repair tools, but there is an open research question whether these tools can repair API misuses. But what is an API misuse? We have an API misuse when the client validates the specification of an API. So the client does not use correctly an API. Here we have a table with categories of APIs that we have found in the literature, and specifically in the MU-Bench benchmark. We consider these categories of API misuses in our work, and we have more details and examples in our paper that you can see. In order to evaluate the repair tools and check whether they are capable to repair API misuses, we conduct an empirical study. To guide our empirical study, we have 3 research questions. First, we want to examine the effectiveness of the tools. Next, we have a sub-question.
Yeah. Maria, we can only see the first slide. Are you moving the slides? Because we are not seeing that.
Yes, I move the slides. You cannot.
No. Maybe you didn't share the full screen. You shared. Yeah. Okay. Yes. Good. Now it's good. Thank you.
Okay. So you can't see the research question slide?
Yes. Now, yes.
Okay. Perfect. And then the next slide, tool selection. Can you see the next slide as well?
Yes.
Okay, perfect. So yeah, I'm saying that we have 3 research questions. First, we want to examine the effectiveness of the tools. Then we have another sub-question for RQ1, where we manually investigate any causes of non-patch generation. Then we examine the efficiency of the tools while they try to repair API misuses. And finally, we evaluate the performance of the tools for different API misuse categories. For the evaluation of the tools, we have selected 14 tools that they are available in the literature. Among other tools, we selected these 14 tools based on our selection criteria. We want to check whether the tools are available, executable, and configurable. In our paper, we detail why we have excluded some tools, and you can check the paper for this. Also for the evaluation, we have created a benchmark, API Bench, because there is no available benchmark of API misuse that we can use to evaluate repair tools. So we selected bugs from 3 existing benchmarks, BEARS, BugJar, and MU-Bench, to create this benchmark. And our benchmark is online in our repository that I will show you in the last slide. To run the experiments, we developed a framework. It is called API-RT. It is easy in general in use. It is executable. It is extendable, and it is provided as a Docker image. And you can also find this in our online repository. Let's answer our research questions now. So first, regarding the effectiveness of the tools, we found that the tools can repair 30% of the API misuses. Most of them, most of the generated patches are plausible, but only a few are correct, semantically correct to human patches. We found that recent tools like Avatar and T-Bar can generate the highest number of plausible patches, but not many patches, but the patches that they can generate, they are plausible, whereas older tools like Loompole, Kali, and Arja can generate a high number of patches, but they are not plausible and correct. Furthermore, we saw that tools that belong to the same framework, like tools under Arja or Astor, can generate similar patches. So there is a high overlapping between among tools that belong to the same framework. In RQ1B, we examined the causes of non-patch generation, and we saw that in most cases, the tools cannot generate patches because of incorrect fault localization, because of technical issues with the tools or issues with the building of the projects for when we repair the API misuses. And also, we had issues with the timeout. Furthermore, we examined the efficiency of the tools. So we found that most of the tools took 4 minutes to generate patches. The earliest tools like T-Bar, Simfix, and Avatar take much more time to generate patches, and maybe this happens because the tools apply plausibility checks, whereas the older tools they don't have such checks. And finally, we examined the performance of the tools per API misuse category. So we found that the tools generate patches mostly for the missing null check, missing value, missing exception, and missing call API misuse categories. The tools take more time to repair bugs that belong to the missing call, missing null check, and missing context categories. So thank you very much for your attention, and you can find the resources regarding our paper online. You can use the QR code on the right corner to find details online, our platform and our benchmark, and you can find our paper in IEEE Transactions on Software Engineering. Thank you.
Thank you. Thank you. We go to Tufik.
Hello. Can you hear me?
Great, great. Yes, yes, we can hear you. Huh? You can go. Mm-hmm.
Can you see my screen?
No, we still see the screen of Maria. Now, yes. Good.
Yes. Sorry. You can see me.
Yes.
So today I'm going to present our work learning lenient parsing and typing via indirect supervision. I am Tofik. I'm a fourth-year PhD candidate from UC Davis. This work was done by me, my advisor, Professor Prem Kumar Devanbu, and Vincent Helendron. So code fragments from Stack Overflow are imperfect. Some of them are fragmentary, incomplete, or ill-formed, like this example. If we look into these examples, there are unwanted ellipses in the fragment. And this type of syntactical error, because of this syntactical error, the IDEs cannot parse this type of fragments properly. And we also found that beginners programmers have trouble with syntax, and they cannot resolve all the issues even after getting feedback from the IDEs. So in this paper, we propose a lenient parser that can parse and type code despite having simple syntactical error. So there is some inherent problem with designing such deep learning model. In most cases, we need some human created data set. So in this paper, we use an indirect supervision approach to generate the data set. We use Eclipse JDT to produce ASTs in scale. And after generating the ASTs, we introduce some form of a very high frequency like syntactical error to the original source code. And while introducing those noise to the source code, we updated the ASTs. So the ASTs will reflect the syntactical error when we have some error in the input sequences. We believe that the transformer-based models can overcome such kind of fragmentation and corruption we introduced to the code. And using such approach, we can actually fix student programs also. So there are two major parts in our deep learning models. The one is block fix that fix the nesting error in the program, and the second one is frag fix that only fix the errors in the fragments. So I will explain these two deep learning based model in the next two slides. So the first one, block fix, that only can fix the nesting error of the program. There is one issue with this deep learning model. We can only feed a certain number of tokens to the model. So in most cases, the Java programs are more than like 500 or 1,000 tokens long, and we cannot feed the complete sequence to the model at a time. The problem with the nesting error or curly braces, it depends on the distant token, maybe 1,000 tokens away. In those cases, it is very difficult for a standalone model to fix those things. So the idea we applied here, we abstract out all the expressions, conditions, and also we replace the identifiers with a generic token. So we have a very reduced vocab. So we can see a abstracted version of the code on the bottom of this slide. So this is the abstracted version we generated from this code. And you can see we have primarily the curly braces and the expressions here. And now we can actually produce such kind of abstracted version at scale. And we can introduce some noises following the distributions the student actually make in their the error they make in their program, and train a transform model to fix those curly braces only. Note that after fixing the curly braces, we can actually rebuild the program because we have initially abstracted out the fragments of the code. So after fixing this nesting error, we can apply our frag fix model that can generate ASTs for us and can also indicates like the syntactical error. And we can use that information to fix like missing semicolons and all other simple errors that doesn't depend on the distant tokens. So please look into the paper if you're interested about this block fix and frag fix model. Here are some examples where our block fix and frag fix model could successfully parse the fragments, but the IDs like Eclipse JDT could not. Like for the first one, there are unwanted ellipses. The Eclipse JDT failed to parse these particular fragments, but our block fix and frag fix could successfully parse it, and it indicates like extra punctuation to indicate these ellipses. In the second examples, you can see some fragments from a switch statement. The IDs cannot parse it because of the missing initial part of the switch case statement, but this deep learning model can actually parse such fragmentary code very successfully. So here are the results we have for student code correction task. We compared it with DeepFix. So DeepFix was originally trained on C, and it could fix program with 400 to 450 tokens. But we have in Java dataset, there are hundreds of examples. There are more than 1,000 tokens. So we cannot actually fit the usual Java program into the DeepFix model that is trained with 400 tokens. So we trained two DeepFix model. One is DeepFix short that is trained to fix program until 400 token, and DeepFix long that is trained to fix until 800 token. And we can see that until 400 token, the DeepFix models are doing great. But after that, our frag fix and block fix model actually outperform both version of DeepFix model and maintain a very good accuracy until 1,000 tokens. So let me summarize the contribution of this paper. We propose an indirect supervision approach to generate the dataset. We have two-stage approach, block fix and frag fix, that can parse the fragments from Stack Overflow and fix student code, fix syntactical error in the student's program. Then we have another model, typefix, for typing the fragments. Please look into the paper if you're interested about typefix. And finally, our approach is language agnostic, so you can easily adapt this for a new language if you can carefully find out the separators of the particular language. So thank you so much.
So it turns to me. Could you see my changing slide? Is it okay? Hello?
Yes, it's okay.
Okay, thank you. Hello, everyone. I'm Xiangxin. Today, I'm going to introduce our new work, Improving Fault Localization and Program Repair with Deep Semantic Features and Transfer Knowledge. This is the outline. Fault localization method is supposed to generate a suspicious file by analyzing different types of features. And the program repair method tries to generate code patches according to the element order from statement level suspicious file. However, there are existing some limitations. For FR methods, they haven't fully exploited deep semantic features, and most of them focus on method level. For template-based PR method, they haven't considered selection orders of repair templates. Thus, we propose the following key ideas to improve FL and PR. Next, I will describe our approach. Let's take a look at the overall framework of our method transfer. In the first phase, we extract methods before and after fix from open source projects and use a syntax checker to generate two large-scale datasets called dataset FL and dataset PR. For FL task, we feed dataset FL to 11 binary classifiers to learn deep semantic features. And for PR task, we feed dataset PR to a multi-classifier to learn the probabilities of different types of bugs. So in the second phase is FR task. For each suspicious statement in the target project, the already trained binary classifiers are used to generate deep semantic features, which are then fused with other two types of dynamic features by an MRP-based model to generate a new suspicious file. And the third phase is PR task. We use historical data to fine-tune the multi-classifier, which is then used to predict the probability of selecting each repair template. We construct two large-scale datasets for FL and PR tasks, but we won't talk about the construction process here due to the time limit. So if interested, you can read our paper or watch the 20-minute video. In FR task, we first use 11 binary classifiers to extract deep semantic features for 11 types of bugs. The binary classifiers are based on bidirectional LSTM. Through such training, each classifier has the ability to identify whether an input sample contains a specific type of bug. Then we use an MRP-based model to fuse deep semantic features with other two types of dynamic features. The model outputs is then used to reorder the suspicious statements. And in PR task, we train a multi-classifier to predict which repair templates should be selected earlier. The model structure is similar with the binary classifier, except for the output layer. The classifier is first trained on dataset PR and fine-tuned on target project. Finally, it is used to predict an 11-dimensional deep semantic feature for each suspicious statement. In this way, the selection order of repair templates is able to be optimized. Next, let's take a look at the experimental performance. The widely used benchmark Defect4J is also used in our experiments. The evaluation metrics and the detailed setups in our experiments can be seen in the table. First, we compare transfer FL with 6 FL methods. As a result, transfer FL performs best on the evaluation metrics, all the evaluation metrics. And then we compare transfer PR with 4 repair methods, and the transfer PR can fix 5 more bugs than the baselines. Next, when transfer FL and transfer PR are used together, there are 47 bugs can be fixed, 6 more than the repair method T-bar. Finally, let me summarize our work. We built 2 datasets, propose the method transfer, and conduct extensive experiments to confirm its effectiveness. And in the future, we will work on extracting deep semantics for more bug types and exploring deep learning-based patch generation. That's all. Thank you. Hello, my presentation is end. So
hello, can you hear me?
yes, we can hear you.
Okay. So I was asking Ye to answer to the first question by Matthias. How well does the synthesis perform in finding plausible patches?
Yes, I have already given the answer in the chat. Actually, we did not look at the possible patches, but I think it's very interesting. But we look at the others, like the compilability. We comparing the compilable, and we look at the more correct patches are generated, and we also look at the ranking information. So more patches are actually ranked in the top 10 than only with the syntactic training, and more patches, the average ranking has been improved, and that's what we have been looked at. But it would be very interesting to add the possibility check in this work, and that's actually something more that we are currently working on as the follow-up work. So I would like to know when it's done.
Thank you. Then we have a question by Gyun-Sik Lim. Please, you can ask your question if it has not been answered. This is about Deer, okay? Okay, this is an accessibility problem. So I have also a question on Deer with David. So basically, I don't understand what are multi-hunk one-statement bugs. Are these, like the same bug reoccurring in several places? Or is it like one bug with several statements that are related either through data flow or control flow?
It's actually one bug that may involve multiple hunks, and each hunk can have only one statement. So that's multi-hunk and one statement bug.
Yes, but my question is these one statements that are in different hunks, okay? Are the statements actually related, or are they unrelated?
They're related because they're all relevant to one bug. They must be fixed together.
They must be fixed together. Okay.
Yeah, in order to fix one bug. Yeah.
Okay. So another question then, I'm curious about the contribution of each idea that Dave gave better results compared to What is the result of a breakdown of the three main ideas? Yes, I actually had this also question about, some kind of ablation study, which one is actually contributing to the performance? Yes.
We actually have a article talking about we did a sensitivity analysis to really analyze like the contribution of each component. I forgot, that is RQ 4 or 5. It's just because of the time, so I didn't put in there. But what I remembered, based on our results, each component can contribute to the overall performance. But I forgot the exact number though. Yeah.
Okay. Okay. Also, another question that I had, general question. I think it's valid for everyone. So I will keep this question of Manish for the end. About patch correctness. Okay. But before that, I also see that you evaluate always. You compare plausibility in DEAR. You also compare. You always compare different approaches in terms of the number of plausible patches that they can generate. So you never talk about correctness.
The correctness, I mean, what do you mean by the correctness? I mean, you mean the accuracy? Because technically
No.
Go ahead,
Because
please.
yeah, because you use test cases, right? To validate that your patch is actually valid, but that's only plausible because your test suite is weak, and then it means that your patch can be overfitting. So you need to check.
Yeah. So basically, we conducted two ways. So the first way is the automatic way, because we have the true label of what developers actually fixed, right? So we know what the developers actually changed. So we actually compare the patch with the actual change. If they match, then that patch, that plausible patch will become the actual fix. But also in some rare cases, we also we have to manually check it, because our generated plausible patches may be semantically equivalent to what developers changed. So we actually manually went through them to check whether that's the case. But in our study, I think we found 3 or 4 in that sense. So so the majority are checked automatically.
Okay, thank you. One last question from you, and then we move on to the others. Lim asked, in order to evaluate the impacts of different factors on DEAR's performance, you use a larger data set such as Defect4G and CPAT minor. From your experiments, can you tell us about the issues and insights you experienced for the separation of data sets?
Could you be more specific? Like what kind of issues or insights you're looking for?
I think he wants to know if there is a difference between your applicability on Defect4G and on CPAT minor, the 2 data sets. That's my understanding. But please, Lim, you can take the mic and explain if that's not it.
Okay, I'll try to answer in general. So basically, go ahead. Someone was trying to say something.
No.
Oh, okay. So basically, I think that Defect4J has been well maintained and has been cleaned, compared with the kind of the large data set, because for example, CPAT minor, it has over 40K bugs, right? So we actually see a lot of different varieties of bugs there. If you're able to see the results, we're only to be able to fix about at most 11% or 50. I forgot, from 15% to from 11% to 15% of the total bugs. So then it's actually, I think that still, even we're better than the existing tools, but I think this field still has a lot of room to grow. also this work can only serve as the kind of the first deep learning based approach try to tackle like the hard problem, which is can we auto fix the multi-hunks and the multi-statement bugs. But actually, that's in the industry. I mean, that's very common actually, because the previous like data sets, for example, like even for DFF4J, some of the bugs are really like a one honk, one statement, right? So that kind of bug is actually pretty easy to be fixed. That's I think that's our experience, and I don't know more. I mean, if you have more questions, more specific ones, I will be super happy to answer them. Yeah.
Thank you. So we go to, I have a question also for Heye. So it seems like what you are doing looks a bit like reinforcement learning, right?
Yes.
Okay. So now when I look at it, I see that your reward here is fully related or fully, associated to compilation, right?
Yeah.
Okay, so it means at the same time that if we have a big like, let's say we want to fix, for example, repair something like Linux, okay, and it takes a lot of time to compile any change in Linux. So do you think that this would work? Because generally we do deep learning because we do training on one batch, and then applying with like testing, it goes fast. So how would this work with your backpropagation if we must compile and it takes so much time to compile every single change that you make to the code?
You mean during the training time or testing time?
Testing time, during testing.
So yeah, that's not our main focus. So the main focus is not about the time to performance. The main focus is like there's a lot of the patches that are not non-compilable, and because there's not aware of the compilations from the compiler. So in that case, if we can increase the ratio of the compilable patches, and then we can for definitely will decrease the time in checking the compilable patches. By that I mean like currently in our experiment we use the bin size of the 200, and then if the 200 already give us like 100 compilable patches, and then less time we can probably to decrease the bin size to 100, and then we don't have to run the experiment to compile all the 200 patches for one bug less time. Did I answer the question?
Yes. Somehow I will come back to you via email. Okay.
Yeah, sure. And I can also give the answer for the general question in the chat about how do we evaluate the patch correctness. So typically we first we wanted if it's compilable, we wanted all the human developers as test suite, and then they will have the possible patches and overfitting patches. And then in that way, in our work, so we actually use our previous work from the DFF4J. We have generated around 4 million test cases independently with on the ground truth, and then we can execute it to identify the overfitting patches. And for those patches are not overfitting, and that our strategy is like to the semantic patches. It follows the previous work. If the previous work has labeled it as the correct patches, and it has been published and has not been has been validated for a while, and then we consider it's a good semantic patches. And if we generate the same as them, and then we will consider it as the semantic patches. And so that's my answer.
Thank you. I have a question for Maria also for API misuses. So basically, API misuses are very specific problems. And if I look at the work of either David or Heye, I don't think that they, even in the design of their approaches, they thought about, you know, this kind of bugs. So I'm wondering if the entire study would not be a bit biased in the sense that, you know, even conceptually, these generic API tools do not even dream of fixing API misuses. What do you think?
Yeah, so based on our study, it seems that the tools are not designed, you know, in a way that they can repair API misuses. So we need to update the design of these tools to identify API misuses like missing calls, for instance, because the tools are so far designed to fix simple, let's say, bugs like missing null checks or missing values, change something, do only very small changes. But if you want to fix a missing call in a sequence of calls, it seems that the tools, they are not designed so far to tackle such issues. So yeah, this is something that I found through this study, and I think that tools like if we use static analysis or machine learning approaches to enhance the tools, the existing tools, and guide the search to identify more complex bugs, including API misuses, it would be useful. I don't know if this is fine for your question. I mean,
yes, thank you. I just wanted a confirmation that this is what you indeed you've seen. Well, that's one of the insights from your work.
Yeah. So it seems the design is not for API misuses. I mean,
yes.
only they can fix only simpler bugs, let's say. That's why our findings show that the tools generate a low number of patches.
Yes. Okay. Thank you. I have a question also for Tufik. So I think yours is a bit of the outlier in our session, at least because it's very close to PL, and I want to understand actually how we can use this for repair. You know, can we learn something about program parsing for repair to help to repair them, or is it just the typing?
It's not for the typing, it's for the for the novice programmers, and yeah, it is not for the repair, like generating patches. So yeah, this is an outlier for this session. I agree with you, and I think it can solve a. Can you hear me? Hello.
Yes, we can hear you.
Okay, thank you. So I think this syntactical error is a small percent of the semantical error that this paper, other papers are addressing. But one of the difference between the syntactical error and the semantical error is that for the semantical error, in the semantical error, you have you cannot get the correct patch in the top one choice, because it's a very difficult problem. As far as I understand, you have to go through hundreds of patches to find a fix for this type of generation task. But this is not suitable for the students. The students are already confused, the novice programmer, so they need something that is can give the solution maybe in top one choices. So I would say this is a bit different problem, a bit easier one inherently, but also required some quick solutions. Thank you.
Thank you very much. Thank you. There is another question for you. How do you compare indirect supervision and self-supervision in generating bugs?
So here we refer as indirect supervision is the data generation process. In self-supervision, if you ask me about this training strategy, our approach is basically self-supervised. So only the data generation part is indirect supervision. Because we use the ASTs, we use the Eclipse JDT to generate the data. I think I have answered your question.
Okay, thank you. And last question from my side to, sorry, yes, Shang-Chi, yes, it's, well, everybody, we agree today that fault localization is a problem in current program repair, right? But I'm wondering if you have looked at semantics-based program repair, like a constraint program repair. Generally, they don't really care too much about fault localization. So did you care to see how you can help them, or whether your approach is purely for template-based and deep learning-based?
Yeah, there are two ways of to fix a bug, which is very familiar for us. And for deep learning methods, the methods are good for extracting the deep semantic features. And for template-based methods, they generally use a predefined fixed template. So I don't think it can very deeply extract the deep semantics. So I think if there is a chance, we will do some future work such as do patch generation automatically with high quality deep semantics. Yeah. So I don't know if I explained it
yes.
clearly.
Yes, it's very clear.
Thank you.
It's very clear. Thank you. So one last question that I have for everyone. So I see that all of you here have relied on test cases, on test suites, for your program repair. The thing is, okay, there is a new research direction, at least that is tries to say that test suites are the test cases that we rely on in our labs are not available in practice. That's why if you look at things such as like what Subfix is doing or like Get a Fix are doing, it's more about in practice, in production, we don't have the test cases. So there is a research line also that focuses on saying, okay, what we have at least is bug reports. So what do each of you think about this? We will start with David Wang. We have 30 seconds. Okay.
Yeah. Sorry, what was your question? Sorry.
Test suites are the general inputs that you use.
Yeah.
It seems to be like it's not an input that is available in practice. So why do we keep using them?
I think first of all, I kind of disagree with you. I think the test cases are still a very important source of testing in the industry. That's actually pretty useful. But I agree with you. I mean, sometimes the people may say that the test cases are flaky and